Review packet, Unit 2 review, take 3. Let's see if we can get this to work. Alright, Unit 2 review, forces, torque, and equilibrium. Those are the 3 topics we studied in this unit. Hopefully I'll be able to go through and get that. Newton's first law, objects maintain constant velocity unless acted on by a net force. Well, this is nothing new. Objects continue doing what they're doing unless something makes them change. On a position time graph, constant velocity is represented by a line. The acceleration is 0 if there's no net force. You've seen this before. If there is an acceleration, then your position time graph is a parabola. Whether it scoops up or down, there are 4 different types of parabolas we've seen. There is a net force, which means the acceleration is not equal to 0. Okay, Newton's second law, the net force is equal to mass times acceleration. Acceleration is proportional to the net force, inversely proportional to the mass, and always in the same direction as the net force. Now, Newton's second law for this unit is used to resolve, you have to resolve the forces in your free body diagram. Once you take your free body diagram and simplify those vectors, you get the net force, and that's usually how you find your acceleration. Of course, you could take the acceleration and use that to get the net force, but that's less common. Newton's third law, every action force has a reaction force that is equal and opposite. Whether you call them action-reaction forces or interaction pairs, you know how this works. So if I'm standing there, I have a force of gravity, my weight, based on the earth pulling down on me. Well, if the earth is pulling down on me, I have to pull back on the earth with an equal and opposite force. Now, the thing you got to keep in mind is that those forces must be equal, even though intuitively it seems like the earth is pulling harder on me because the effects of the earth are more noticeable. So that's the idea, that it doesn't matter how hard the earth pulls on me, I have to pull back with exactly the same amount of force. And those forces never cancel out. Action-reaction pairs always act on different objects. The only way for forces to cancel or balance is if they're acting on the same object, and this does not happen with Newton's third law. So if I have a TV on a table, that table pushes up on the TV with a normal force. Table on, well, it's not really a book, it's a television. I'll get that fixed here in a second. Table on TV. Well, the TV returns the favor. It has to push back on the table with exactly the same amount of force. They are equal and opposite. Those interaction pair of forces are always equal and opposite. You will never get the earth pulling on me harder than I pull back on the earth. And they never cancel out because they are acting on separate objects. I can't emphasize that enough, although I probably just did. Universal gravity, F equals big G m1 m2 over r squared. This should be familiar. This will help us describe the force of gravity between any 2 objects in the universe. For example, the sun and the earth. We need to know the distance from center of mass to center of mass, r. We need to know the mass of the sun, the mass of the earth, and of course big G, which you determined in the Cavendish experiment, right? Those are the things we need to know in order to calculate the force of gravity between any 2 objects. Now, what's interesting about it is that we can use universal gravity to show how the acceleration due to gravity does not depend on the mass. For example, if I take a big book and a crumpled up piece of paper, they will fall at the same rate, and this is why. Acceleration does not depend on the mass. On the surface of the Earth, or near the surface of the Earth, the force of gravity is m times g. Well, anywhere in the universe, the force of gravity is big G m1 m2 over r squared. Get the squared in there. Well, yeah, there it is. Okay, good. Now, there's my mass. I am one of the masses over there, and it doesn't matter which one because you're multiplying. And so because I can take away a mass on either side, I get acceleration due to gravity is big G times the mass of the planet you're on divided by the radius of the planet squared. Of course, if you're in orbit around a planet, the force of gravity is going to be slightly less, but it will still be there. Okay, torque. Torque is equal to R, which is the distance from the fulcrum, times the force applied, distance from the axis of rotation. And in a teeter-totter or seesaw problem, that would be the fulcrum. F is the force applied, and of course the sine of the angle. Now, there are two types of torques. There's clockwise torque, which makes things spin that way. We abbreviate it CW, and counterclockwise torques, which spin the other way. I think uh, lefty loosey, righty tighty, I think is what I remember when I was a kid. Um, Equilibrium. Now there are two types of equilibrium we saw. One was the free body diagram type of equilibrium where there's an object suspended and the net force is zero. If you know the mass and the angle of that rope, you can determine the other vectors involved. You can find both tensions. The upward or vertical part of the tension is equal to T sine theta, and it's supporting the weight of the box or the object that's being suspended. So T sine theta, the vertical component, supports the weight, and so it's equal to the weight of the object. Of course, because there's no motion, it's floating there. Well, floating isn't the right term. It's just sitting there. The horizontal component, T cosine theta, balances what we could call T2, that horizontal tension that's attached to the wall. Those two have to be equal. The horizontal forces have to be equal and the vertical forces have to be equal because it's in equilibrium. Now, one thing to keep in mind, sine and cosine change as you go from 0 to 90 degrees. When your angle is less than 45 degrees, the cosine is bigger than the sine, as you probably know. If your angle is bigger than 45 degrees, the sine is bigger than the cosine. That's something you should keep in mind. As your angle gets closer to 90, the sine gets bigger than the cosine. Now, net torque. The seesaw or teeter-totter problem, depending on where you grew up. You've got a distance on the left. That's how far from the fulcrum or the axis of rotation. You've got a distance on the right. Let's say 4 times the distance. Well, that means the force that's applied on the left has to be 4 times bigger than the force that's applied on the right. You could use the torque equation, RF sine theta, but you have to assume for these types of problems that theta is 90 degrees. So if I have 2 meters on one side and 6 meters on the other side, that's a ratio of 3, which means that if I apply 10 newtons of force on the right side, I need to apply 30 newtons of force on the left side. Again, this isn't about equations, it's about ratios and making things equal. And in a multiple choice question, they would be nice numbers. Okay, free body diagrams. The horizontal free body diagram, most straightforward. You got a box on a flat surface and the tension is going to the side horizontally. There's no angle. There's a tension, there's usually friction, and of course we can't do any of these without a mass. Those are some of the things you'll know about these or maybe you're looking for. Now there are two types of horizontal free body diagrams. There's a constant velocity and there's an acceleration. If the object is being pulled with a constant velocity, that means the tension is equal to the force of friction. If the object is accelerating, then the tension minus the force of friction is equal to the net force. And you can use that value to determine the acceleration of the object. So again, constant velocity, everything's balanced, tension and force of friction are equal. Acceleration, the tension minus the force of friction is equal to the net force. That's your typical horizontal free body diagram. Next up is the sled. The only difference between this and the horizontal is that you're pulling at an angle, theta. This does change things. Anyone who's pulled a sled knows that if you pull up, it's a little easier to drag that thing across the floor. In this case, the normal force is not equal to the weight of the object. Remember, if you're pulling up, the normal force is not equal to the weight because you have an upward pull from that tension that helps support some of the weight. So the tension times the sine of the angle contributes to supporting the weight of the object. So the weight is equal to the normal force plus Ft sine theta. Now the consequence of that is that because the normal force is smaller, the amount of friction is smaller because, of course, as you know, the force of friction is equal to mu times the normal force. So that upward pull reduces not only the normal force but also the amount of friction. Ramp, gotta love the ramps here. So in a ramp problem, the force of gravity or the weight of the object is always going directly down. We can often and should resolve those into the two components. One component goes into the ramp, wait for it, into the ramp, and that's the weight times the cosine of the angle. That's always equal to the normal force in a ramp problem, always. The other component of gravity goes along the surface of the ramp, and that's the weight times the sine of the angle, and that's usually what causes the object to move. Now, in this example, we're assuming that there's no push or pull up the ramp, and to be honest, if it were a multiple choice question, this is typical of what you'd see because, you'd have to do more calculations if you had something pulling or pushing up. So the weight of the object times the sine of the angle is causing the acceleration. Now, resisting acceleration is usually friction, force of friction going up the ramp, which is equal to mu times the normal force. And so in a sense, the force of friction also depends on the weight of the object, indirectly, of course. So these are some of the variables you will encounter in this problem. The weight of the object, well, I'd probably give you the mass, the normal force, the force of friction, mu, and the angle. Those are some of the things that you'll need to think about when you're trying to resolve this problem. Of course, knowing the mass and the angle are most of what you're going to get, mass, angle, and probably the coefficient of friction, and then you can get all the rest of the numbers. Atwood machine, big A is the large mass, B is the little mass. The weight of object A is always going to cause the acceleration. In an Atwood machine, there's no other choice. It's the big object that causes this thing to move. And so the weight of object A is responsible for the motion. The weight of object B is resisting the motion. It's the only thing that's trying to slow this down. In order to get your net force, you have to subtract. So the weight of object A minus the weight of object B is your net force. Well, Newton also says that the total mass of the system, ma plus mb, is times the acceleration is also equal to the net force. So you have two of those values. It's really easy to find the weights, and then you just do a little bit of algebra to get the acceleration. Actually, once you plug in the numbers, it's not really algebra anymore. It's pretty much arithmetic, which I think you can handle. In order to get the tension, I'm going to get started on it. In order to get the tension, I usually take the lighter object, the loser of the tug of war. So the tension minus the weight of object B is equal to the mass of object B times the acceleration that you just calculated. You could use object A just one extra step algebraically. Over the edge problems, you've got a hanging mass. I'll call it object B just for kicks. It could be anything you want to call it. It could be an unpronounceable symbol. But the weight of that object is responsible for the object moving, or for the system moving. So the weight of object B is causing the motion. And what makes this different than an Atwood machine is that it's not the weight of object A that matters, it's the friction on object A that matters. So the force of friction is the only thing resisting the motion in this situation, which means you have to know the coefficient of friction, unless that's what you're looking for. So the force of friction is resisting, the weight of the hanging mass is causing. That's how you're going to get your net force. The weight of object B minus the force of friction is equal to the total mass, ma plus mb times a. Very similar to an Atwood machine, the only difference is you're not dealing with two weights, you're dealing with a weight and friction. To find the tension, tension minus the force of friction on A is equal to the mass of A times the acceleration that you just determined. Remember, it is friction that's resisting the motion, not the weight of object A. The weight of object A is only important in determining the normal force because we use that to calculate the force of friction. But the weight of object A does not contribute to the motion in any way other than it helps determine the friction indirectly. I had a little bit of trouble with copying and pasting. I was going to do the elevator thing, and then I realized that I already had it set up on another page, so we'll get there in a second. Copy and paste, cloning, wait for it. There we go. 3 elevator situations. There's an acceleration up, which means the net force is up. Remember, in the second law, net force and acceleration are proportional to each other and always in the same direction. Now, and then of course constant velocity where the net force is 0, and acceleration down where the net force is pointing down. So, for the first situation, if the acceleration is up, the net force is up, it's because the elevator is pushing harder on you than the Earth is pulling on you, which I think is pretty straightforward. So in the end, when the acceleration is up, when the net force is up, you feel heavy. So you step on the elevator, you push the button to go to the top floor, it starts moving and you feel heavy. And that's because the normal force of the elevator pushing up on you is bigger than your weight. And if you were standing on a scale, it would read more than your normal weight because the net force is up. Normal force bigger than your weight, it has to overcome that force of gravity on you in order to accelerate you up. In between, constant velocity, net force is 0, everything's balanced. A scale will, you feel normal, a scale will read your actual weight. Normal force is equal to your weight. Acceleration down, typically that's when you get to the top floor, the elevator slows down, the net force is down, which means that you feel lighter. Why do you feel lighter? Because the normal force is smaller than gravity. Normal force is smaller than gravity. In all 3 situations, the weight is the same. If you have a weight of 750 newtons, it will always be 750 newtons. It doesn't matter if you're going up, down, or constant velocity. It's the elevator's force acting on you, that normal force that adjusts based on the acceleration. Now, astronauts in space feel weightless not because there isn't any gravity, because we know the moon is in orbit and that's much farther away, but because there's no supporting force. There's no elevator pushing up. There's no floor pushing up. There's no bathroom scale that they're standing on. In other words, they're in free fall. So weightlessness means there's no supporting force, not the absence of gravity. Now, the Ninja Squirrels production thing. I was trying to draw a stopwatch in class one day, so I drew the stopwatch. I put the buttons on top, and I drew the little window for the time, and it looked like a ninja squirrel. And of course, the loop for the string, and so I turned it into a ninja squirrel, just for kicks. Gotta have fun with this stuff, right? Thanks. That's pretty much it.